Hey everybody, it's Pat and Frankie here from Engine Power. What you're about to watch is one of our favorite projects of all time. It is absolutely the wildest, craziest thing we have ever done, and this is content we specifically picked for you guys to air on our new channel.
This is from the beginning to the end, the whole deal, and I'm very excited for you guys to watch this because this is off the chain. It said it couldn't be done, but we did it.
Yeah, so make sure you hit the subscribe button, make sure you hit the notification bell so you get updates about new episodes, and enjoy.
You're not gonna wanna miss it.
You're watching Power Nation.
Hey everyone, welcome to Engine Power. Today we have a very special project in the shop that we have been teasing you about, but today it is time to start building.
And we have a really special guest in the shop, Nitro Funny Car driver, superstar, and U.S. Nationals champion, Tim Wilkerson. Tim, you have been hearing about some of what we've been doing, and now you see all the parts, so I'm glad you're in the building to experience this.
Well, I was looking around to see if Caps was behind me. You said superstar for a minute there, but oh, I appreciate that.
Yeah.
I tell you what, who doesn't like a Big Block Chevrolet, right? I mean, they're a neat deal, and we build a lot of them in our machine shop for people, and they're just a great motor to make horsepower with.
Yeah, well, you can see that, we're doing something a little special because we have two of them and enough parts to build two of them. And I don't know if you've done any twin engine stuff. Have you done anything where it's identical engines?
Well, believe it or not, we do a lot of tractor pull motors for people.
Oh, yeah.
And most of them are blown stuff, but we see a lot of that stuff. And I am always amazed at how they can put all that junk in one pile and stuff don't fall out the sides. I mean, they got all those boxes and hookups and amazing. But yeah, this will be pretty neat. But I was wondering why we have two.
Well, the big thing with engines, one of the things that people always ask, if you have two engines and you have all the same parts and you build them exactly the same way, will they make the same power? Well, yes and no.
Yeah, right. I mean, top fuel funny car, right? We have 6 motors in the trailer at any point in time. You are betting on taking one out, putting the other one in, putting the same tune-up in it, hoping to God it does the same thing.
Yep, engines have their own personality.
Oh, yeah.
It's all on their tune-up, stack tolerances, a whole bunch of subtleties. They'll make close power, usually not identical. So one of the things we're gonna do is we're gonna build 2 identical engines, and we're gonna dyno them to see if they make the same power. But what else would you do besides a tractor pull with 2 engines?
Boy, I don't know that I do much else with 2 engines, to tell you the truth, besides, like you say, our stuff is so unique to its own application that this kind of stuff, you're looking for 5, 10, 20 horsepower, and it will be interesting to see, put all the same parts in all the same pile, see how they work.
Yeah.
Well, we're gonna do one better than that. One thing that people have never seen before is we're gonna dyno these separately, but then we're gonna dyno them together.
End to end.
On the dyno.
That would be really cool. Wow, that's the craziest thing I ever heard.
I was afraid you were going to say that.
What's your dyno people say about something like that?
Well, I don't know if they are extremely they're curious on our
one, I would think they
why
would be.
Would we want to do that, and 2, well, the reason why we're doing it, there's a lot of things we don't know, and this, if it works, is going to teach us a few things about how engines, if they're coupled together, what they will do. Because literally we just don't know.
Sure. Do they work together? Like you said, is engine A counting on engine B to do the same thing, or is it pulling it backwards?
Right.
Right. Well, I would expect that that would be a problem, but it'll be really interesting to see.
Well, it will, and we have a lot of good parts, and as I say, everything is identical for each engine. We have 2 Big Block Chevys. They're actually honed the same. All the parts are going to be the same. They're going to be put together the same. And because of what we're doing, we want to make the engines last, so we want to put some good parts in them.
Well, I can see that. I mean, there's name brand parts, the same kind of stuff I run in my funny car. Felpro, Total Seal, ARP. If it'll work in my car, it'll work in this. You take all this stuff and, hey, get it right out of some catalog, right? You get that stuff, and anybody can buy this stuff.
Yeah, this is all off-the-shelf stuff. We got every single piece from Summit, and that's a great place to go where you just, if you need everything to build in a complete engine, you can get it all there. So that was a huge help.
We spent some time, digging through and picking out exactly what we wanted. Start off 4340 forged cranks, right? You got to have something that's going to last. Those are 4.250 stroke, and we have a big old piston here.
Yeah, look at that big booger.
Yep, the 4310 bore, forged, nice, heavy duty, a little bit of a dome on it.
Sure. Yeah. Well, like you say, what kind of compression is this thing going to have?
These are going to be 10, almost 11 to 1.
Okay, so it's pump gas.
Pump gas.
Yeah, it's still going to be pump gas, but I mean, like you said, really nice parts. Total seal rings, a nice forged rod, nice intakes, nice heads. Trick flow 320 heads. So they're going to make some pretty decent power.
Yeah, I mean, I see you got some ATI balancers on them. You got all kinds of neat stuff like that.
Yeah, so, you know, because of what we're doing, I mean, at some point we may separate the engines. I'm hoping. I'm
hooking them together.
I'm hoping at some point they'll always stay together.
Hooking them. Once you build them in twins, it's like, I can't break them up.
Yeah, they're all of a sudden they're a couple.
Well, that's one of the things I was noticing about all, you know, the higher quality parts that are here. I'm thinking to myself, boy, for a 500 or 600 horsepower motor, that's a lot of nice stuff.
Yeah. Well, times two. We just wanted them to be the same because if at any point we want to test different things on identical engines, like say maybe you want to put a power adder on one or a different power adder on the other, we can do a whole lot of things, but it's just nice to have two inventory. I would love to see them together in a vehicle.
Well, I was standing here thinking the same thing. We need if Frankie had an old pickup truck or something. I don't know where he would sit after we put them together, but
right on top. We'll build a seat. Right on top.
Wouldn't that be neat if we could find something to put them in?
I would absolutely love that. You know,
I've seen some old hot rods like that. You know, twin engines.
Oh yeah, back in the '60s. Oh gosh, that was a big deal, wasn't it?
Our application is dual dynoing right now, but these would be at home just about in any vehicle that you would want to run on.
Sure, yeah.
And I don't know, you can run a torque wrench.
Oh yeah.
So, I think that maybe enlist you on some help with one of these.
That'd be fun. Sure.
And
sure.
Well, the talking's the easy part. Let's get to working.
Great.
With the blocks freshly cleaned, our twin Big Block Chevy extravaganza can begin. All right, Tim, well, we got that block all cleaned, so now we can move on to mock-up, because with a lot of parts comes a lot of pre-work before you can actually go to assemble. So, I mean, you know that. You have a ton of experience with that.
Yeah, I mean, like you say, you buy all these parts and you just assume they're perfect, right? But we're not ever going to assume that when we build a motor.
Exactly.
We run into the same thing in our car. We'll buy it. I mean, I'm using crazy round numbers here, but 500 connecting rods, and we'll take every one of them apart, put them all back together and check the clearance in them, kind of what you're up to here.
Yeah, and like this block doesn't even have the cam bearings in it, because when we're doing mock-up like this, not that you're expecting to find problems, but you always want to plan for the worst case scenario. So, you know, checking main bearing oil clearance, if you have to adjust something, it's better to just have the cam bearings out in case you have to, you know, take the machine shop and get a line hose.
Yeah, sure. If you're going to stroke the thing with a line hose, it's going to get all kind of grit and garbage back inside of it. You have to clean it again. Don't need any chance of that getting back in your cam bearings.
Yeah, you sitting behind the back.
Yeah.
I had a question, because I kind of wanted to know just for fun, but what do you guys run for main bearing oil clearance on your stuff?
Our cars are, there's such a ridiculous scenario in what happens with our vehicles, but you know, the application we use this for, this block is aluminum, so it's growing like a banshee, right? I mean, it's getting bigger as it goes, but ours usually have anywhere between 5 to 7. The rod bearings are the same way, they're 5 to 6.
Wow.
I mean, huge oil bearing clearances, but you're not talking about 0 weight oil either, you're talking about a 70 weight race oil. So we're running mud through a big hole.
Something to take
for lack of better
the
terms,
load,
right?
Yeah, something to cushion the load on it.
Yeah, but the load is so terrible. I mean, we have cylinder pressures that most motors can't dream of.
Yeah, and when you're doing this, I think a lot of people, part that they skip or the part that they might not realize is that the prep work. When you're doing the prep work, you have to do it just like you would during assembly, because that's the most important part, you know?
We're going to check this thing front to back, make sure all the clearances are correct.
Sounds like you've done it a couple times.
Yeah. Well,
engine building shouldn't be guesswork.
Nope.
It should be, we should work pretty much in absolutes.
Right. Even in our engines, we actually have a complete motor sheet. I wish I would have brought one.
Yeah.
You would be amazed at the stupid stuff that we write down.
It's not stupid.
You know what I mean?
It's all data.
Exactly.
I'm a data guy. He's a data guy.
Yeah.
So that stuff, you know, on an aftermarket setup like this, stuff is very, very close tolerances. They go the extra mile because they know how the parts are going to be stressed more. They know things are going to be run harder. So the accuracy of them, you know, a lot of companies go through great lengths to make things accurate.
Right. Well, you got some high quality parts too. That's going to make a difference.
After cleaning the bearings and bearing saddles, we'll install standard bearings, starting with number 5. We'll apply ARP Ultra Torque Lube to their main bolt kit.
Now you're a funny car guy. That's what I was hoping to see.
The caps get torqued in 3 equal steps to 100 pound-feet. With the rear 2 main caps installed, we use the sun and dial bore gauge to precisely check vertical oil clearance. The rear came in at 3 thousandths, but number 4 came in a little tight at 24 10,000ths.
Well, we know this one's 2.4, right? We sure like this clearance in the back one a lot better than we did number 4. So
like to make it match.
Yeah, so how can we fix that?
Well, we do have a set of standard X's. Normally when we're building something, we'll order a set of standard bearings and then a set of standard X's, or extra clearance.
Right.
Which I'm sure you guys do that all the time, trading bearings around to get different clearances.
Yep,
So.
in the machine shop I do that.
Yeah.
You can throw a dead cat through the clearance in our fuel motor, right? We don't care.
Yeah, we don't, that part, yeah.
That thing we don't care about, but this
yeah.
thing we want it to be correct, right?
Yeah, exactly. And I think we get that question sometimes is how do you correct that? If you have too tight, what can you do to correct that? And I think one of the ways is, an easy way is to have an extra clearance bearing where basically if you use both bearings, it has 1/1000 extra clearance over the standard.
Oh, so we're just going to put half a shell in it.
Yep, yeah, so we can just put a half in it and it should theoretically raise it up to 2.9, which is really close to 3, within a tenth of the 3 thou that we want. So we have a set, we can put that in, and
what side do you want to put that on then, since you're using half of it?
Location is really important when you're doing that because you want the thicker bearing always on the load side. Now, at the parting lines, there's not going to be a ledge because they're really close inside. You're talking about a half a thou, but usually you want to put the thicker side on the load bearing. So on this one, it'll be on the cap side or the bottom side where the crank's going to load. Yeah,
so pushing. Okay.
Yeah, so we'll do that and see what she measures up at.
Let's get this thing knocked apart.
Yep. After swapping the bearing in the block for an extra clearance one, we can reinstall the cap, torque it up, and see what the vertical oil clearance comes in at.
Because of the bearing's construction, you're not putting a big ridge in it. That's the big misnomer. People think there's going to be a big ridge at the parting line. There's not. It's only a half thousandths difference.
And it's okay to do this because we've measured the crank. We know that the journal isn't really big. It's just a combination of parts. So doing this
it's the main housing's on the low.
Yep.
And the crank's mid to high.
Mid to high, yeah. So you get what you get.
Just what it is. Look at that.
Look at your math magic there, my friend.
Math magic, 2.9.
2.9.
On the nose.
That thing's almost dead on what we want it to be.
Yep.
Right. As far as what we're doing here, I think we got a handle on it, and I know that you have stuff to do as well.
Well, you guys, I think that I've tutored you along long enough for you to finish a job, right?
I think we can figure it out.
I mean, you guys have forgotten more about building motors than I probably will ever know.
I don't think so, Mike.
I tell you, the applications are just what you said. I love that saying that you have, Pat, that most everything we do is application specific. Well, I tell everybody that about our car. It's good for absolutely nothing but what we use it for.
Yeah.
Right? So you got this under control?
Heck yeah.
That's yours now, my friend. I'm going to go back and I'm going to find me a funny car to work on because
you got stuff to do.
I got junk everywhere at my shop. Thanks a lot, guys. I appreciate you having me.
Go get to
you,
work.
Sir.
Thanks a lot.
Appreciate it. Now that we've got our main bearing oil clearance all set where we want it, we can move on to the connecting rods, and we're going to use the same rule, 1/1000th per inch of shaft. For these engines, we opted for an upgraded rod bolt from ARP made of L19. We'll torque them to achieve the appropriate stretch and then check our vertical oil clearance. The King rod bearings have a coating for extra protection. All the oil clearances come in between 21 and 23 10/1000ths. Next, we'll file our total seal rings for both engines. The gaps are set at 32 thousandths on the top ring and 35 thousandths on the second ring. We chose this specification so that these big blocks are ready for anything we want to do with them later.
Get out of the way.
Whenever you're ready.
Am I in your way?
Whenever you're done.
Okay.
An easy way to keep the rings in order is to leave them in their respective bores after they're finished.
With ring filing done, we're ready to install the pistons. These use a single spiral lock on each side, which means there are 32 to install. It takes a little patience to get them into place, but the more you do, the easier it gets. While Frankie cleans the bores, I'll load up the pistons with our Total Seal ring pack. These are 5/64ths, 5/64ths, 3/16ths in size. Using the Goodson piston ring installation tool simplifies the process. When cleaning the bores, we alternate between lacquer thinner and transmission fluid until the rag comes out clean. Even if the block has been final cleaned, there's always some debris in the bore. We can finally begin assembly, starting with the King Racing High Performance main bearings.
With the rear main seal installed, they receive a coat of assembly lube. Then, the Eagle 4250 stroke crankshafts are dropped in. They are forged from 4340 steel, giving them excellent durability. They were balanced by our favorite machine shop, Shacklet Automotive Machines.
That sounds really weird.
Having two Matco digital torque wrenches makes it easy to torque the main cap bolts in 3 equal steps to a final value of 100 pound-feet.
To get the compression ratio we wanted, we chose a set of Icon forged 4032 pistons. They have a 23cc dome and coated skirts. The Eagle H-beam rods are 6 385 center to center length with full floating wrist pins. All the components have been labeled for their respective engine and location, so all we have to do now is drop them in. Go ahead.
Before final torque, we make sure the fasteners are completely loose. This gives the most consistent torque and stretch values. The rods are torqued in 2 steps to their correct stretch at 100 pound-feet.
Yeah.
8 pistons down, 8 more to go.
With our crank, rod, and piston assemblies in both blocks, it's time to look at everything else to finish out the short blocks. Now, these are a relatively tame set of engines, but that does not mean we're not putting quality parts in, and that starts with the camshaft. We have a cam kit here from Howard's. We've decided to go with a hydraulic roller, and the kit comes with the cam and the corresponding lifters. As far as specs, we'll get to those later. Along with that, we've picked up some double row timing sets. These are billet gears with a 9-position crank sprocket so we can dial in our cams where we want them. Since we were missing some timing covers for this operation, we picked up some polished cast aluminum ones from Summit, and they look awesome. In addition to that, we needed some great balancers for this build, so we have some ATI Super Dampers, and these have a double keyway provision, and that is going to be very important later on. For our oiling system, we found something very cool. This is Summit Racing's Pro Pack Oil Pan Kit, and it comes with everything you need to get your oil system set up. We have a 6-quart oil pan that is clearanced for our 4250 stroke, and it has a screen and scraper already inside. Also a 1-piece oil pan gasket, a new high-volume oil pump, and the pickup that matches the pan, and it even comes with a chromoly drive shaft with a steel sleeve. Now we can continue with the installation of the camshafts. At 50 thousandths lift, the cams have 236 degrees of intake duration and 242 degrees of exhaust duration. Lobe separation angle is 112 degrees. Lift at the valve is 634 thousandths at the intake and 641 thousandths at the exhaust.
Before going any further, make sure to install the 2 threaded oil gallery plugs.
Our twin Big Block Chevy build continues with Summit Racing's Billet double roller timing set. It has a 9-keyway crank gear so we can adjust our cam's intake centerline.
Before we can degree the cam, we have to find true TDC. And to degree the cam accurately, this measurement needs to be precise. Because we want power lower in the RPM range, the cam will be put in at 103.5, which is 8.5 degrees advanced. To make these engines pop, we'll go with gloss white. Now that the cam is locked into place where we want, we can install the thrust button. Roller cam conversions require a thrust button to control the forward movement of the camshaft. The ARP fasteners are torqued to 25 pound-feet. A fiber gasket is put into place and a touch of silicone is added for extra insurance. Then the heavy-duty cast aluminum timing cover is bolted on. After getting some thread locking compound, we'll lightly screw in the ARP oil pump stud. We've already checked to make sure it does not interfere with the back of the main bearing and has proper thread engagement with the oil pump installed. The oil pan kit comes with a copper gasket. The high-volume oil pump can be dropped on next. We'll apply some ARP Ultra Torque lube and tighten the fastener to 65 pound-feet.
For proper engine operation, the oil pump pickup clearance must be correctly set. Using a straight edge, we measure down to the oil pan rail on both sides of the engine. It averages 7 3/4 inches. We'll measure the oil pan depth, which is precisely 8 inches deep. The gasket is 1/8 inch, giving us a clearance of 3/8 of an inch. Perfect. With some silicone on the gasket, the oil pan goes on for good. It's secured with an ARP bolt kit. We have reached a great stopping point on our twin Big Block Chevy build, and I must say, so far so good. They're going together very well, but we still have a ton of work to do.
We're going to get to that next time though. We'll be putting on our cylinder heads, the rest of our valve train, getting our engines sealed up, getting them on the dyno, and I'm really excited to see if they make the same power or not.
But that is the easy part. The next engineering challenge we will have is coupling the engines together on the dyno. That coupling has to be rigid enough to transfer the power, but be easy enough that we may get to use it in a vehicle.
We'll cross that bridge when we get to it though. For now, this is a good day's work.
To learn more about this build, go check out PowerNationTV.com.
Here in the Engine Power Shop, we are back on our twin 496 cubic inch Big Block Chevy build. These engines are being built virtually identical to each other, and so far we've got them to short block status. The plan today is to wrap them up with a bunch of great parts from Summit Racing Equipment, get them in the dyno room, dyno them individually, and see how close they are on power.
Then comes the hard part. We are going to attempt to couple the engines in line and dyno them on the dyno at the same time, and that creates its own unique set of challenges.
Today we'll get started by installing the balancer and timing pointer, then setting true TDC on the balancer. These adjustable timing pointers make it easy to set and lock into place.
With our head gasket and cylinder head combination, we have a calculated compression ratio of 10.27 to 1. Thread sealer is required on the ARP fasteners because the bolts go into the water jacket. The bolts are torqued in 3 steps to 70 pound-feet. Next, the tie bar style hydraulic roller lifters, which are included in the Howard's cam kit, get lubed and installed.
After aligning the supplied guide plates, we put thread sealant on the trick flow rocker studs. Sealant is required because the studs intrude into the intake port. Our trick flow push rods are 3/8 in diameter and have an 80 thousandths wall. They are 8/800 long on the exhaust and 7/900 long on the intake side. High pressure lube goes on both ends, then they are slid into place. For rockers, we're using Trick Flow's full roller aluminum design with a 1.7 ratio. Because we're running a hydraulic roller camshaft, preload is set to 1/2 turn past 0 lash.
With RTV laid around the coolant ports and on the china walls, the intake manifold goes into position. The ARP stainless steel intake bolt kit receives thread sealant because some of the bolts intrude into the lifter valley, which could cause oil leaks.
With the valve train lubricated, they are covered with a set of polished cast aluminum valve covers from Summit Racing. Summit Racing's polished aluminum electric water pump will handle the cooling. Our induction is finished off with a Trick Flow 1-inch tapered 4-hole spacer and a QFT 1050 CFM annular discharge carburetor.
Before we dyno the 2 big blocks together, we need to dyno each of them separately to see how much power they make. That's slick. First up is what we consider Engine A. It was primarily built by Frankie, so he gets to run the controls. After our standard timing and fuel adjustments, we'll make a final run. These engines are going to be all done before 6,000 by design.
Yeah, I mean, we didn't want something that's going to turn, 65, 7,000 RPM because theoretically when we're done, we have 2 of them. So whatever they make should double.
Wow.
Wow.
is
Torque heavy.
very torquey. Torquey.
Wow. 629 for torque and 596.7, which 596.7 is at 5,500.
All right.
Peak torque is at 4,500.
Nice. Now, you can see it's trending down, right? People always want to run these things way past where they're making power. There's literally no reason for this. If this thing is trending down because of the size of the intake tract, because of the size of that camshaft, this thing is designed to be literally done by 6,000. So
I mean, yeah, with a camshaft, it's 236, 242. That's the same camshaft we put in a 410-inch Mopar, and now we have it in a 496 Big Block Chevy. Yeah, torque 1.27 per inch, power 1.20. I mean, that's good for the size cam, size intake, heads, all that.
Pump gas.
So now the question is, got to get engine B on and see, see if it makes the same.
Okay, so that's the question. Okay, so we made 596.7. If B makes 620, something's going on.
Something's really wrong.
Engines are going to be relatively close because they are the same parts. We guess that they'll be within 10 or 15, but if it crests that 20 mark anywhere, either one engine's bad and one engine's good or whatever. So let's see what engine B does.
All right. The change from engine A to engine B was quick because they are essentially the exact same power plant. We'll put the same tune-up from our previous dyno run into engine B.
Because humans worked on this, right? There's going to be subtleties in all kinds of different things. From the carburetor to the oil pan, everything in between. Plus
tolerances, things like that.
The goofballs who clicked them together. So, all right. So,
see what she does.
Same exact pull. It's like we never took the other engine off. It looks exactly the same.
You wouldn't be able to tell just by looking at it. So.
That's close right there, my friend.
That's pretty good, yeah.
Yep, 632.7 pound-feet of torque, 607 horsepower, two completely different engines, almost the same result to a very, very small degree. You know what I call that? Deja vu. I know. I can't believe I actually said that. No, but it's the truth, right?
It's worse than the dad jokes.
That is a horrible joke, and I admit that, but it kind of fits it because we've done two completely different things. You screwed one together, I screwed one together. B team did make a little more power, I'm just going to say, but that's
there's some other stuff going on there, maybe, but
maybe I didn't.
There's obviously some subtle differences going on inside the engine that you would have to account for and check for.
There could be. No, they weren't exactly identical on compression. There were subtle differences.
Very slight
How
difference.
The manifold lines up, how the manifold was cast. Who put the boosters in the carburetor at what height?
Booster height.
There's a whole bunch of different stuff. But what I can say is we have engines that are very, very close. All right.
All right.
Happy times.
That was fun. That was interesting. So now we move on to the hard part.
All right, I have to admit, I am impressed on how close they made the power.
Yeah, I mean, being that close with the same selection of parts, less than 2% difference. I mean, I think that's kind of cool. I mean, like you said before, we could fuzz them and get them closer if we wanted to, but I think for what we're doing, that's going to be just fine. And now we have to move on to hooking them together, which I kind of have an idea on how to hook the cranks together, but there's a bunch of other stuff that goes with that: water, fuel, power, all that.
We could pontificate about it all we want out here. Let's just roll it in, get it close, and
start
see what we can
mocking it up and see what we need to do.
I'm gonna get trapped here.
I can get most of it.
All right, good. Oh, look at that. Ooh. Wow. That's
pretty nice.
That's really nice. See, with the actual carts being the same crank height, that's going to be okay, right? If as long as the engines are level.
Yeah, because the flanges, the
cranks
are going to be perfectly in line on the center line. You just have to make sure that, left to right, they're straight, but that's pretty easy, I think.
So first order of business is hooking the carts together, where they're the same height down here, and there's probably a few different ways to do it, but with that pad making it actually a very consistent fit across it, you could probably bolt straight through.
Yeah,
we could
through that hole.
build something in some sort of spacers and brackets to bolt that straight through.
And that bar is already drilled and tapped because that's where the hooks go to latch the cart in. So that might be something where I think they look close, but we can check to make sure maybe the holes in the side where the pins go for the handles, if they go all the way through, might be able to just put a bolt through there, and that would keep them left to right and forward and back. That would hold them in place together. So that would be nice. It'd be an easy way to do it. So.
Yeah, because obviously one of the major concerns is the engine moving around out front, which if it's bolted solid there, I'm not worried about it. Water lines look pretty easy.
Yep, just Y off and come to here, Y on the bottom. Fuel lines, I think we can just connect straight through. There's plenty of fuel flow for that. Throttles, just make a rod that goes, control that one and then make a rod that connects to this
hooks
one.
to these, okay. That's okay. So the major.
Yep. Exhaust will be easy, I think. Just
the exhaust.
Just piping, you know.
Exhaust. The major thing will be the coupling. Now, you had a great idea that we discussed. That was one of the things of the 10 things that we discussed. Yeah. We don't want these. They can be coupled by like a rubber drive shaft coupler, right? Because that's pretty popular when the engines are in a vehicle, but I don't want that flex in there because of what we want to do. I want to mount them rigid for a couple of different reasons.
Yep. But I mean, those drive shaft couplers, they work normally, mostly when I've seen them in vehicles. The engines are right up against each other, so it makes it really easy. You don't have a lot of distance in between them, and they're usually like small block Chevys. I mean, I'm kind of worried about those with the power transfer. I mean, yes, they will give it some flexibility, but I'm kind of worried about them actually holding up to the power, and because I've seen them fail in stock drive shafts. You know, even in stock cars in the drive shafts, they have torn and come apart and stuff. So those, they would probably work. Maybe. I don't think we were going to chance it, and I think we had talked about phasing the engines, and for that, I don't think they're going to work.
Right, but so we need a spline shaft. We have to build something that bolts to the flywheel on this, kind of like our drive plate does, and then have the same opposite receiver that's bolted to the front, which is rigid. And that's
something that's spline that we can clock.
Right, and that's why that front, that's why this is double keyed. We went ahead and did a double keyed balancer, and that's the reason why. Same like for like a supercharged application, a lot of torque on that. Now sometimes blowers, like a Roots type blower,
like an 871.
Yeah, it takes like over 100 horse to run. But we're going to put 6 times that amount through it, right?
Yeah.
So this is all set to go. You had a great idea on how to couple these together with some stuff that's simple, and I like the sound of it.
Well, yeah, because I wanted it to be. We could get custom stuff made. We could make some CAD files, send them out, have some custom stuff made. It would probably fit great. It would work great, and we wouldn't really have to engineer too much. But I wanted to keep it simple. Use some off-the-shelf parts, and consequently keep the price way down. So I think for relatively cheap, using off-the-shelf parts, the idea I had was to use a mini spool and some just regular old 31 spline axles, like out of a Ford 8.8 or something like that, because then it's rigid and it's easily, you can get them pretty easy, easily accessible, easy to get, and I think with a little bit of work, we can make that with, have Jimmy maybe cut up a drive plate for the crankshaft and a drive plate for the flywheel. All that should be pretty simple and easy, and then with a little bit of welding, we can make that work, and it's going to be a solid. It's going to be a solid coupling, and I think it's a lot of power to transfer. But I think if you think about like when a car launches, that's a lot of force going through that axle, and so I think that's going to be the easiest way that will hold up to the abuse that we're going to put it through.
And we talk about phasing, right? If you spline it, that means you're allowed to phase the engine, and you probably I already done the math on that. At 31 spline, you take that's 11.61 degrees per spline. So
okay, so if you do 4,
that's 46.45 degrees.
Yeah.
Say you want to phase the engines where you fire number 1, you want to fire this one, roughly 45 degrees later. Well, we can get that within 1.5 degrees.
Yeah, exactly.
And I think that's to learn the things about engine phasing or coupling at what firing order. That allows us to do that because now with splines we can switch the engines to where we want.
Yeah, and we can do it accurately. Something that's not
very accurate.
Not going to flex, something that's going to be rigid, and so that if it does make a difference, we're going to be able to clearly see it and say yes, it made a difference, or no, it didn't.
It just has to hold the power. Now I'm positive it'll start and run.
Oh yeah.
But making a full tilt pull with 629 pound-feet, that has to go through the front of this one now at that point. And another thing is, as a concern, that has to be good because if that fails, you know what's going to happen to this engine.
Yeah, that one's going to bog down, and this one is going to try and run to the moon.
It's going to
full
put
tilt,
it in orbit. So we have to get our kill switch right, which is easy. And I think that I think this is going to be interesting. But the first things first, we got to get our stuff figured out. Just literally coupling the carts together, and then we'll work on our drive system. But I think we have a quasi good plan.
Yeah, start taking measurements, start making some stuff, and go from there.
I can tell you this: from the back of the flywheel to that is within the irometer's capability of measuring it at 10 inches. Perfect.
Yeah, that's nice and short. That'll be easy to make, but also not so close where it's like hard to get in there and do it,
No,
so I think that'll work.
If you have a shaft, the longer you make the shaft, the more twisty it is. But
keep the torsional rigidity good.
Yep.
So, all right, well,
at this point,
stop talking and
let's
start doing it, I
see what we can
guess.
do to hook the cart together.
Yep.
We'll begin with the easy task, splitting the water lines on the top and bottom. To do that, we'll use some 1.5-inch OD tubing to make a couple of simple T-joints. The joint is welded together and a hole is opened up for the water to pass through.
The next plumbing we'll tackle is the exhaust. In order to effectively evacuate it from the dyno room, we'll fab up a system that joins both engines into a 5-inch outlet. This should be the last mock-up of this
Oh, no, this is...
piece.
What? Ooh.
I had built it like that.
Put it down.
For room, but now
Put it down.
Visually, I kind of like that.
That'd be like if it was in a vehicle. Hold on. Let me.
Tighten that up. It looks level.
Kind of like that.
Yeah, visually, I like that. I mean, it does make a difference. So, in terms of how it works.
Well,
I like how it's level. It's like you said, it's how it would be if you had it in a vehicle or something.
Probably. Well, if the vehicle was 8 feet wide.
Yeah, and probably would have, made this a little bit nicer. But for now, this is going to work.
I do have now concern because of how much pipe it is, how it merges, how that's on the back. What if this thing, we know how mathematically how much it should make if we double the power. What if it makes more? Or what if it makes less?
It could. You don't see now we have unequal exhaust, but we also maybe have a scavenging effect on the back engine because of the momentum this air is going to carry.
Well, we're tying them together at this point, right?
Yeah.
Now, if you tied both carburetors together with a common plenum box, then they would be.
Then it would be a V16.
Then it'd be a V16. Yeah.
Yeah. I don't know. That'll be interesting. I don't know. I guess we'll find out.
Well, this looks good. The other side is you're one down, one to go here.
Yep. The other side's kind of started, but still gotta get this fully welded and then get the other side done.
I'm gonna take this back off.
After the exhaust is test fitted, it can be finish welded. While we work on that, Jimmy King from the carcass shop cut out both of our drive plates on his CNC plasma table. These will bolt to the balancer and the flywheel and are made from 1/4-inch mild steel.
Next, the hub for the flywheel side of the drive system is made from half of a mini spool for a Ford 8.8-inch axle. We machined a register in it so it would fit precisely into the center of our flywheel drive plate. This ensures that the plate is completely flush when the two pieces are tacked together. Since the drive assembly will endure extreme abuse, it is welded on both sides. Now we need to determine the right length for the axle shaft that will connect the two engines together. Drive plate to drive plate, so if the end of it's there and that is flush, that is right on 9.5. We'll cut 10.5 inches from the Summit Racing 31 spline axle shaft. Then back to the lathe to put a register on the axle so it fits into the drive plate.
Before we can tack the axle to the balancer drive plate, we're going to make sure that both engines are at TDC compression stroke on the number 1 cylinder. With the bolt holes aligned and the bolts snugged down, we'll mark and scribe both pieces to ensure correct alignment. Then the piece can be tacked and fully welded on both sides in the lathe.
All right, fully welded up, even though it's a plasma cut plate of hot rolled and a cut off axle, it's within 0.02 of straight after it's welded. So
that's pretty good.
Yes.
I mean, the heat's even all the way around, and like you said, working with a 1/4 inch plate that's just cut on a plasma table, you know, so within 2 thou, I'll take that.
Yeah, I'm just gonna barely touch it to face it off. I don't want to take any structure out of it, but we're just gonna get it so it's flat.
Yep, so it mates up flat and everything's straight.
Then we're gonna let her buck.
Cool, well, one more piece, kind of done.
Oh, this is big time, because now
we have both ends.
Now we can phase the engine.
Yep.
That was the biggest thing.
They'll be at top dead center, and then we can phase them from there, so.
Yep.
All right. To mount the 2 carts together, we're going to keep things simple. 1/2-inch holes are drilled in the rear cart, and the splines are slathered with extreme pressure lube. We fabbed up 2 spacers out of 6061 aluminum. They slide onto a set of 1/2-inch grade 8 threaded rod, and the 2 engines are carefully mated together.
All right, there's that side. That's okay. All right. Next, the coupling system is indicated across 3 planes to make sure that everything is in precise alignment. Both fuel lugs are connected with a number 8 Earl's line. A rod with hymens connects both carburetors. Using our handmade T-joints, the front engine is tied into the water system and everything is sealed up.
Okay, so this is about the point where you start to think, maybe this isn't such a good idea. Maybe we're insane.
I mean, I still think it's a good idea because we haven't done anything yet. But
I mean, yeah.
The one thing that this is probably going to protest is the start.
Yes, because you have now twice the cubic inches, and these are pretty stacked on dynamic compression, and it's still one standard Big Block Ford starter.
All right.
So,
well, no time like the present. I guess fuel
wasn't too bad.
Oh my! I was kind of hunching there for a second. I'm like,
but they're both running.
That's 2 engines running.
That's smooth too, like, you know, not shaking, not moving, anything like that. We got a nice rigid mount.
We'll see what a partial throttle pull does. Then maybe we'll go to half throttle.
Oh boy.
There we go. Just watch, just make sure nothing's on fire. Okay, made a pull.
It did it. It didn't do anything. I didn't see anything.
No, that's fine.
Oh, wow.
Okay, that's fine. Right now, that was probably quarter throttle, right?
Yeah. And 628 pound-feet.
628 pound-feet, 311 horsepower. Yeah. Obviously, we know what the engines make.
Yeah.
All right.
Wow. I mean, nothing looked crazy. The engines didn't move around a ton. They're nice and solid. No parts came out. Nothing's leaking.
It's a rarity that a dyno run gets my heart racing, but this one actually is.
Yeah, that one was, I mean, you're just waiting.
Just waiting for something bad to happen.
Waiting for something bad to happen and hoping it doesn't, so.
I'm going to go half throttle.
Yeah, go half and we'll see what it does there.
Oh, hold on to something.
Oh, boy.
Oh, boy.
Still look good.
It broke 1,000 pound-feet.
Whoa! Wow. That's, oh man.
That's half throttle. 1,017 for pound-feet.
Yep.
At 3,600. Again,
wow.
It's half throttle.
Half throttle. And I mean, yeah, manifold vacuum, we're only monitoring on the second engine, but manifold vacuum is going up to like 4 inches.
They're going to be the same. The
So,
engines
yeah, they're going to be the same, but that, I mean, 4 inches, and it's making.
When I saw that thing
1,000.
crest 1,000 pound-feet, about jumped out of my seat.
Yeah, I didn't see it. I was looking in there, but I mean, nothing looked crazy. Again, it looked
Oh, my
smooth. The
God.
engine stay.
It's time for the big Magombo. What do you think?
Do you think we should check anything first, or just go for it?
I'm
I'm gonna go in there.
I'm
gonna go look.
Go look at that shaft. Make sure everything's okay.
Yep, make sure nothing's crazy.
All right.
Just double check everything.
Ooh,
All right.
doggy.
If anything is likely to fail, it's our drive system. So we'll give it a quick visual inspection and check all of the fasteners. So far, looks good.
How far are you gonna ring this thing out?
We are gonna now do a pull like there was only one engine. So just like we did before, 3,000 to 5,800.
All right.
But they're hooked together.
They're hooked together. This is the first, literally the first time we're doing a wide open throttle pull. So
This is the
this
first
could go
full
super bad or super good.
Yeah,
We have
so-
zero idea.
You guys got a helmet?
You guys be ready?
Yeah,
Be ready.
This is, I mean, this is full on. I'm nervous. Like
It's cool.
I'm sketched out and nervous at the same time because
What about you two?
I don't know.
Y'all nervous? I'm not nervous.
I'm fine, really.
All right, well,
Behind
let's
the
go.
safety glass. Yeah, we're
3
good.
to 58. You all right? You're actually freaking out right now.
I am freaking out. It's
All right,
I'm ready
you'll
to dive in
grow
there.
out
I
of
guess.
that
but-
eventually.
You watch for flames.
Yeah, I'll watch for parts and flames. You watch that, I guess. Let's do it.
No time like the present. It did it! It did it!
Oh my God!
I was watching the
Sweating
RPM too.
All right.
Holy crap!
That is not bad.
Not bad.
1,212 pound-feet, 1,162 horse.
Holy wow!
Now,
Oh my
now,
gosh.
mathematically, it should double the engine rate. But again, we have two different things going on here, right? That we
So
don't.
you're gonna find where you lost that horsepower.
Well,
right?
we're going to find that. That was.
Try.
Somewhere.
I
got two options.
I mean,
I am rarely nervous during a dyno pull, and
That
I'm
was-
like, oh my God, what's going to happen right here?
oh my gosh!
I think it's worth another pull. I mean, y'all don't build things to break them.
No, I mean
It's
we,
not gonna
we don't.
break.
The
That's
proof is
it.
in the pudding, right?
Right.
Sure.
I mean that makes me want to go in there and check
The
everything.
engines are fine.
It's not the engines.
The drive system's what we're worried about.
Yeah.
You know,
Oh,
you know, to actually set a record, you have to do one pass, then you got to follow it up.
Right.
Go back up and
So-
overload
What is it?
that
One
with
can be a
with a
fluke,
single
and
engine.
two is proof.
Yeah.
All right, so this is God, I can't believe that worked. All right, so
Hold on a second. Hold on. Both of y'all stick your fingers out right now. How about that? You're
they
kind of
shaking?
shaky.
Anybody,
A little
anybody
bit.
who's been watching the show knows that I'm shaky anyways. You should see me weld. It's like this, you know?
See?
It doesn't even
We
care.
could do
doesn't
this
even
all
care.
day.
Doesn't
Yeah.
even care.
Wow.
1204 1167.
Okay.
There you go.
Not practical by any stretch, but man,
This is
that's
obviously
pretty cool.
not practical by
none
any
of this
stretch of
is
the
practical,
imagination. Alrighty, guys.
Holla at
You
you.
saw it. You saw it
Well
live.
done. I mean, it's like a first. There you go.
Looking at peak values, engine A made 596.7 horsepower and 629 pound-feet of torque. Engine B made 607.5 horsepower and 632.7 pound-feet of torque. Adding those numbers together, we get 1,204.2 horsepower and 1,261.7 pound-feet of torque.
Taking our highest peak numbers from our double dyno runs, we made 1,167.1 horsepower and 1,212.2 pound-feet of torque. When we subtract our combined single dyno results, that puts us down 37.1 horsepower and 49.5 pound-feet of torque from our ideal expected result. Still, it's almost a pure doubling of power and torque compared to the single engine runs. We're only down 3% on horsepower and 4% on torque. We're not certain why yet, but we expect that the combined exhaust and perhaps engine phasing could be big factors.
Okay, so
man.
it didn't double the power and torque.
Mathematically, no, it did not make double or what the two engines made added together.
Right.
And I think there's a few reasons for that. I started to think about that already, and I think probably the biggest one is the exhaust. We talked about this before, the exhaust being hooked together.
It's tied together.
It's tied together, 4-inch into 5-inch. We did that because it's the only way that we can get our tubes on and evacuate it, and not contaminate the room.
Right.
And so I think that might be a huge factor in this being down on power like that.
If you look at it though, I mean, as far as how far they're actually down.
Oh, it's not much. I mean, it's.
Oops, there. Let me get the right one,
Yeah,
Pat.
get the right one. I saw 60 pound-feet total, which is 30 per engine.
Okay, so it's down.
Okay, yeah.
It's at 1,162. So
37.7 horse.
yeah, so it's down 37 horse, 15 per engine.
Yeah, 15 per engine, which is totally believable for exhaust.
Because we're running it hotter than we were dynoed.
Yes, because we dynoed them a little bit
yeah,
cooler.
so we dynoed them cooler.
Yep. Plus the exhaust.
Plus the exhaust, and I mean we're at 12. It should be 1260.
Yeah, I mean, 40. What is that? 48.
That's 20 pound-feet.
Yeah.
That's damn close.
I would say for some of the things we had to do to make it fit in the room and work with our setup, I mean, you could really dive into this a ton more, and we talked about that,
We can.
equal length exhaust and equal length headers and all that.
The biggest thing, we have the rig now
Yes.
that we can do it anytime we want. And just the fact that it's just like one big giant engine right now.
That's, oh man. This
992 inches of Big Block Chevy.
Nobody thought they would ever say that.
Now, that's an interesting one, but
Wow.
we literally have two engines, nothing fell apart, everything worked.
Yep.
1,162 horse
Wow.
at 5,200,
Yep.
1,212 pound-feet,
Right at 4,700.
right at 4,700.
Wow. That just goes to show, it's not about what engine you have, it's about how many you
How
have.
many engines you have? Yeah. Okay. Some people like power adders. I'm an NA guy, right? So
Yeah.
some people like turbos, some people like nitrous, some people like blowers. I just like adding another engine.
Yeah, it's just more cubic inches.
That's the ultimate power adder. Another engine. So.
Oh.
All right.
Wow, that is great success.
Happy times. To learn more about this build, go check out PowerNationTV.com. I don't think the pipe length off the back is a concern as long as we don't contaminate the room.
Yeah, I think if we just cut it right in front of the Y, I think we have enough tubing to make it go all the way to the back, and I think it'll keep it pretty clean in here. I think it'll work.
I like it. Hey everyone, welcome to Engine Power. Today we are getting back on our favorite and probably the craziest thing that we've done in this shop in a while. If you're not familiar with what you are looking at, these are two 496 cubic inch Big Block Chevys, and they are hooked together and have been ran on the same dyno at the same time.
Now that we have a coupling system that we know will work and handle the power, we can never leave well enough alone, and today we are going to make some changes to hopefully improve power and most definitely learn something. The first thing we're going to try is splitting the exhaust system. For packaging purposes, when we built the system, we had both engines Y into one piece of 5-inch, and that could be a restriction, so we're going to split those, make them independent, and that could hurt power, could help power, but there's only one way to find out. The second thing we're going to do is actually change the phasing of the engines, but we'll get to that later and explain how we're going to do that. For now, let's get started on the exhaust. After removing our exhaust, we'll start by cutting off the Y connection. We'll add an extension to the rear engine and reinstall our S-pipe for the front engine. This allows us to slide on some 4-inch flexible exhaust tubing, which extends to the exhaust plenum.
I'm not gonna lie, this does make me a tad bit edgy. Now it's just a regular dyno session, only with two engines,
Except for two engines,
and
but-
some drive system that you welded.
I'm only kind of worried now. Did it do something?
I don't know.
I thought I saw maybe, but
Okay, well, okay, so we have a little more torque.
yeah.
1,217 pound-feet and 1144 for horse. Now,
Which is actually down.
the horse is down by a little bit. It made 1167 before.
Overlay that with the last one we did.
Okay, it's trading off back and forth. Made the pull fine.
Yeah. I say it ran just the same, so.
Carburetors look fine.
Let's back it up, see what it does.
Double engine exhaust mod, take 2.
Yeah, see if it prints the same numbers.
Maybe just need a little heat in it.
Yeah, get some more oil temp in it, I guess.
Okay.
Okay, yeah.
Yeah.
Wow.
A little more consistent. Notice how the graph is like
Super smooth,
super
right?
happy. Yeah, and we'll take it. 1162. I mean,
That's pretty close to the 1167 that we had before.
Definitely up on torque.
Yeah, I think that's a
twice.
solid. Yeah, it's twice and 8 pound-feet with some good oil temp in it, so.
Yeah.
Wow.
The graph looks better.
I would call the exhaust splitting a success.
Me too.
Is it a dramatic change?
No.
But I would say that is a good success.
I would say that the graph looks better. We are going to continue doing some testing on our dual big block dyno setup, and so far it's yielded some interesting results. We have split the exhaust into 2 separate systems, and it was pretty promising. So we are going to continue on by phasing the engines different, meaning we are going to change where they fire relative to each other. Our drive coupling system that we have created was specifically designed to make this an easy task, and so far it's held up pretty well. So we are going to continue on. In their current configuration, both engines fire the same cylinder at the same time. This means that when engine A fires the number 1 cylinder, engine B is also firing the number 1 cylinder, and this continues throughout the firing order.
We are going to rephase the engines to be offset as close to 45 degrees of crankshaft angle as we can get. This means that cylinder 1 of engine A will fire, and then 45 degrees later, cylinder 1 of engine B will fire. Engine A cylinder number 8 will follow, and then cylinder 8 of engine B, and so on. This essentially recreates how a V16 works and hopefully will show a difference in power.
We'll start by putting both engines at 45 degrees before top dead center on the number 1 cylinder. Then we can disconnect the drive axle from the harmonic balancer.
So much easier to turn over now.
Where there's only 1 engine. Next, the front engine is rotated to true TDC, and now all we have to do is rotate our axle until the bolts and splines line back up. Since it's been disconnected, the drive axle is dialed back in for runout.
I'm interested to see if it changes the way it starts, because
I hope so.
Before we had 2 cylinders trying to be compressed at the same time, and it was a little hard on one single starter, so maybe it'll be better this time?
It needs all the help it can get.
That's for sure.
Let's see if we can get her lit here. That is better.
That's better.
That is better.
Definitely better.
It sounds
a little different, yeah. It's hard to hear, but it definitely sounds a little bit different.
Oh, it definitely sounds different. Theoretically, if it makes power, it makes more power. Say it all of a sudden makes 1,260 pound-feet and 1,200 horsepower. I'm going to say I planned that and I knew that was going to happen, but that will be a complete lie.
If it does, I will be pleasantly surprised. And will we be able to logic it out? Yes. But if it doesn't, will I be surprised? No.
I am literally going to say I meant to do that.
Sure. Okay.
That is an improvement.
That is big.
1,229 pound-feet of torque. But look at the horsepower, 1,183.4.
Wow.
Now, if they were dead on, it'd be 1,200.
Yeah.
That is extremely close.
That is close. Overlay that with the old one, because that's peak numbers. But I'm willing to bet that it's probably everywhere. To be that big of a spread.
I'm sure it's up everywhere.
That is. Wow.
Let's make another one on it just to say we did, because we made 2 on the first one.
Yep, back it up.
Maybe with the heat and all that stuff. All right.
Try her again.
1232, and it's a power's down 1179.5.
Yeah, just down a few.
Just down a few, but
Yep. Wow.
wow, that told us something right there. Okay,
That is interesting, right?
so that's I mean that's
Wow.
10 to 12 pound-feet.
So we're not making more horsepower,
No.
but somehow phasing the engines has freed up horsepower in terms of pumping losses between both engines. Not even stop with the phasing. I mean, we're like right now we're at 45, but well, what if you're at 15? What if you're at 30? What if you're 180 out?
What if
You know?
what if you're 180 on the opposite?
Yeah.
There's so many
There's
things.
so
I
many
mean,
options or things that we could try.
that is
That's crazy
This
though,
this
right?
was one of the most interesting things I think I have ever done. I've done lots
Yeah.
of R&D in my career.
Same.
One thing I've never done is had two engines at the same time hooked together.
I still can't believe that what we built works. At first I was really sketched out with it, because I had to weld it. But
I
now
was
we've
very
made several
sketched
dyno pulls on it. I feel really comfortable with it. Now I just want to try more stuff,
Now we want to try
Wow.
more stuff. Well, that is going to be left for another time. But
Yep.
as for now,
Still, great success.
happy times.